All right, there were some questions about the due dates on the labs. So let's talk about that.
The rough draft is due tomorrow for the synthesis lab, right?
It was originally,
Oh,
but I can move it to Thursday. Some people wanted it.
all right, cool.
Are we turning in pre-lab and all this stuff too?
No,
No pre-lab?
no pre-lab.
Very nice.
So the rough draft turn on Thursday. Turn in on Thursday.
Did more practice. More practice.
All right. What else? What other labs do we
Qualitative
have?
analysis.
Qualitative analysis.
Also do Thursday.
Yeah.
All right.
Also do Thursday.
Everything Thursday.
That's informal one, right?
Yeah.
The 2-pager.
Yeah.
Right.
Well, maybe more than 2 pages, depending on how many equations you have to write out.
Right.
Wow. 2 parts.
2 parts.
And our test is this Thursday too, right?
Yeah. Exam 18 is this Thursday also. We have the, remember the pH buffer lab? pH buffer lab, just leave that in your notebook. I'll check your notebook sometime. And then we have the Le Chatelier's equilibrium lab. You can leave that one in your notebook too, unless you already filled out the form. Was that it?
Pretty sure.
Yeah.
Probably.
All right. Are there any questions on Chapter 18? So the pH titration you're going to turn in on Thursday. That'll be the rough draft we do on Thursday.
Wait, so we have 2 rough drafts, one for the synthesis and one for the titration.
Oh, no, sorry. pH titration is not due yet.
Okay.
pH titration, we're going to go into the computer lab to plot out the data. And then after that, we'll have a rough draft due. Or probably no rough draft. No, not tomorrow. Tomorrow we're doing a experiment. Which experiment is that? And it's the rate, and is it in your lab manual?
No.
No.
So we're going to put it on the classes then?
It's a handout experiment. It's supposed to be a handout experiment, but it's not in your lab manual. Well, we're going to make it not into a handout experiment. We're going to just do it tomorrow together in class.
Are we going to do both days? Tuesday and Thursday?
No, just one day. We'll do it all in one day. It used to be 2 days because the first day I had people record what we call the visible spectrum of the crystal violet solution, but in this case it's much quicker with the new equipment that we have versus the old stuff. Okay. All right, so it's still a busy day in lab. Okay, are there any questions or none? Chapter 18 stuff.
I was thinking about the figures.
Okay.
Okay.
TJs. All right, what's your question?
Oh, never mind. Never mind.
All right, then we're going to continue with the kinetic stuff, the speed of the reaction. We talked about the graphs before spring break. And we talked about, did we talk about the patterns that we see, the 3 patterns?
Yeah.
All right. And did I call them anything? All right, we'll start off with that.
Second order, first order.
in this chapter, you're going to see three characteristic patterns, and when we're looking at the reactants versus time, and the first one is when the reactant is consumed linearly, like this. It's just straight line decay or straight line consumption. We look at the slope. Is the slope changing at all?
No.
No. And so what we have here is the negative of the slope is what we call the rate. And so the rate is constant. It doesn't change. And so there's something called a rate law. And the rate law shows how the rate changes with concentration. And in this case, we have something called a zero order dependence. Because the rate, actually, let me see. The rate just equals K. Now K is a constant called the rate constant, and it would be a constant for a given reaction. And so we know that the rate is just equal to minus delta A over delta T. And so K is just the slope or the rate of reaction, the negative of the slope of the rate of the reaction. All right, so this is where the term zero order comes from, because it has a zero order dependence on A. In other words, the rate doesn't change with A. The rate just stays constant. And so there's no dependence on A. Then we can define this. When we look at this, this is just a linear line, y equals mx plus b. Right? And y is the concentration of A times T. M is the negative, actually, M is the slope here. Is minus KT plus concentration of A times 0. All right, this part is called the rate law. The rate law tells us how the rate changes with concentration. This equation here is called the integrated rate law. And this equation tells us how the concentration changes with time, or how long, what kind of time interval is required to hit a certain concentration. The way we can get the integrated rate law is by using the rate law. And that is, what we can do is we can derive the integrated rate law in two ways. One, we could just derive it graphically. The way we do a graphical verification is we try to fit the data points to a mathematical equation. That mathematical equation is a straight line. Okay? This is a process called curve fitting. Curve fitting. When we do curve fitting, we try to overlay a straight line on this and do something called a linear least squares fit. The linear least squares fit tries to fit this data as best as it can with some mathematical equation, minimizing deviations from it. And we generate that equation for that line. The other way we can do this is we can take the rate law and just rearrange that. And so here our rate law is K is equal to minus delta A over delta T. Delta A is just A final minus A initial. Delta T is just T final minus T initial. We'll take the negative of this whole thing. Now, A final we call A times T. A initial we just call A times 0. And so this is the same thing as saying A times t minus A times 0 over t at time t minus t0. You know, t0, usually we start these experiments at 0 seconds or 0 minutes. And so we end up with this equation, and then just rearranging this equation, we get A at time t is equal to minus kt plus A times 0. And so we could use a little bit of math to do this. But basically we want these two equations because with these two equations we can predict things. So what kinds of things can we predict? Well, the rate law allows us to predict, you know, what the slope is at any concentration. The integrated rate law allows us to predict the concentration at any time. Therefore, we can figure out what the slope is at any time. We can figure out the slope or the rate at any time by using the integrated rate law to figure out what the concentration is, and then using the rate law to figure out what the rate is. Or, you know, how long it takes to consume a specific amount. And so, two ways to get the integrated rate law: either use some math or use some more math, either do it graphically or algebraically, like we just did over there. All right. This is for what we call zero order. The next type of pattern we observe is going to look like this. And it's easy to draw because what you do is you cut it in half, and then you see how long it takes. We call that T1 half. And then cut it in half again, and then see how long it takes. So in this case, in this pattern, each successive T1 half interval, like cut it in half, takes the same amount of time, T1 half. Cut it in half again, another T1 half. And so all the T1 halves are equal in this pattern. That's different than the previous curve we looked at. When you look at a straight line, what happens, you know, when we cut it in half? Can you look at the previous graph and see? When we cut it in half, it takes a certain amount of time, and then we cut it in half again, so we're at 1/4. What happened to the time interval? For a straight line, what happens to T1 half? Successive T1 halves. So what I'm asking you to do is just eyeball it. You know, just take a look. If I had a straight line, a linear line, and I cut it in half, let's say it takes this long, right? And then I'll cut it in half again and see how long it takes. Does it take the same amount of time or less time? And then cut it in half again. And repeat it. Cut in half again. What's happening to the time interval? Is the time interval staying constant?
It becomes a half less each time?
Yes. Yeah. One thing is, if it's linear, each successive one is smaller. And then if you look at it, it looks to be half as big. And so each time we cut the concentration in half, the half-life gets cut in half. Whereas over here, each successive half-life of the time interval stays the same. When that's the case, this is what happens to the slope. And so if we look at the initial rate here, you know, that would be the tangent here, and then compare it to the slope here, and then compare it to the slope here, we see that the rate is decreasing. You know, it's getting slower and slower, the reaction. this. And so the rate is not constant here. In fact, this is what we call first order decay, in which the rate is equal to K A to the first. And so here's where we get the first order dependence. We'll just call it first order with respect to concentration of A. With respect to A. And so what's happening with the slope here is if we cut the concentration in half, you know the slope gets cut in half. You can see that mathematically here, but that's what's actually happening on this graph. And so if we have 1/2 the initial concentration, then the rate is equal to Ka at time t. And so this will be A at time t. We'll substitute that in here. We'll get K 1/2 A initial, which means we'll have 1/2 the initial rate. 1/2 the initial rate. And so each time we cut it in half, it takes twice as long. Next one, because in other words, we'll have half the initial rate. So this tells us how the slope, this is delta A over delta T. Now slopes are always, rates are always positive, so we'll take the slope and multiply by -1, make sure it's positive. And so this slope is always changing. In fact, the rate is decreasing. And so this is always changing. And so if we try to do the same thing we did last time, it doesn't work. And so here, this would be the minus of the concentration of A times T, or final. So we'll just do it exactly the same. Minus concentration of A initial divided by T final minus T initial. And then we solve for A final. What's the problem with doing that? So we get A final, which is going to equal A times T, which is equal to, etc.
We don't have a constant rate.
We don't have a constant rate. That's the problem. Since it's always changing, it's getting slower. And so we can't use this simple algebra. Since delta A and delta T is always changing, what we have to use is calculus. And so there are two ways we can determine the equation for this line. We can do a curve fit. And so we just try different mathematical functions that might match this. Do a linear least squares fit to see which one's best. Or we use calculus. Or actually curve fit or calculus to get us the equation of the line. Linear lines are easy because we know the equation of a linear line, but this, what is the equation for this curve, this line? We're actually going to do neither. We're not going to use curve fitting and we're not going to use calculus. Because somebody else did it for us. And so basically the derivation in calculus, we'll just do dot, dot, dot. And so the equation for that curve is this. It's going to be ln of a times t over a times 0 is equal to minus kt. This is what we call exponential decay, or exponential consumption reactant. This slows down exponentially. This is what we call the integrated. Integrated comes from calculus. But this term is based on the derivation, how it was derived, so we don't really care about that. All we care about is that we have this, and the rate law, and this. Having the integrated rate law allows us to calculate the concentration at any time t, or how long, the time interval required to reach a desired concentration. And having the rate law allows us to figure out the slope at any concentration in this curve, and hence the slope at any time, because we could use the integrated rate law to figure out the time. And so these are the two equations that we need. To fully define this. Okay, that's first order. And then we'll take a look at the second order. Second order is going to have a different curve to it. So if we track the concentration of reactant versus time, we'll see that to consume half the reactant here will take a certain amount of time. Let's say this, we'll call that T1 half. Then to cut it in half again, so we start over, cut it in half again, what is the time interval it takes here for the next half-life? So the first half-life takes this long, the next half-life takes a longer period. And if we measure it carefully, we'll see that the second half-life is actually double the first half-life. And so if this is 1 times, this would be 2 times previous. And with each successive half-life, we double the amount of time. Therefore, this next one will take twice as long as the previous one. Yeah, yeah. And so it decays very slowly. And we'll see this in the slope, because if you look at the slope here, if we look at the initial slope, what we call the initial rate here, and then compare it with this one, we'll see a 4-fold decrease in the rate. And that is a second order dependence. And so the rate is equal to K, which is a constant, times the concentration of A squared. And so this is A times T. If A times T is 1/2 A times 0, we substitute it in there, then the rate is equal to K times 1/2 A times 0 squared. So 1/2 squared is 1/4, so we get 1/4 our original rate. 1/4. That shows a second order dependence. A times T. Okay, so this is our rate law. Unfortunately, we can't solve for the concentration of A at time t here using algebra. Because the rate, as we recall, the rate is just equal to minus delta A over delta t. So the problem with delta A and delta t is it's always changing. You know, this is always changing. And so it might have been good at one time interval over here, but by the time you get to this time interval, is the slope the same? No, it's totally different. And so, again, you can't use this. When this is always changing, we must use calculus. And so again, there's two ways we can determine the equation for this curve. One way is by curve fitting. The other way is just calculus. Curve fit. If we use calculus, then we get the integrated rate law. It looks like this. 1 over A at time t is equal to plus kt plus 1 over A at time 0. And so this will allow us to make predictions, you know, about anything we might want to know. So it's important to know what the order is. Because if we know what the order is, then we can understand how it decays, and we have the equations that define that, you know, how it's consumed. So let's talk about determining the order of the reaction. What are the ways that we can determine the order of the reaction? Method one is we can eyeball the data table or the graph. If we eyeball the data table or the graph, let's look at the data table. Normally when you collect data for an experiment like this, you know, we would have time versus the concentration, say. And so we'll have the initial concentration here at 0. And then what we'll do is we'll look, you know, about how long does it take to get approximately 1/2 the initial concentration. Sorry, if we go 1/2 times the initial concentration, you know, that's T1/2. And then we look at, you know, when we get to approximately 1/4 of the initial concentration, and there's another T1/2. And so what might happen between the successive T1/2? Well, one thing that might happen is it stays the same. So the first T1/2 and the second T1/2 are equal. If they're equal, then what order is it? This would be well, not zero, I'm going out of order. First, which order is equal. The other thing that could happen is it takes half as long. If it takes half as long, then it's zero order. Equal. The other thing is it takes twice as long. If it takes twice as long, then it's second order. And so what we do is we just try to eyeball the data table. If we start off with 1, we're looking for a value around 0.5. How long did it take? Let's say it took 6 seconds. And then we go from a value around 0.5 to 0.25. Let's say this first interval took 6 seconds. The second interval here took 6 seconds. That tells me it's got to be what order?
They're first order.
First order. First order is they're equal. Let's say the first interval took 6 seconds and the second interval took 12 seconds. What's the order? Second order, yeah. If the first interval took 6 seconds and the second interval took 3 seconds, it's got to be about
Zero.
It's got to be zero order. And so those are the three possibilities you have. Here we don't have to graph it, but we could graph it. You know, if we graphed it, then you'd see it. Something like this. Or we just do this. Do this. Okay. Versus something that looks like this, where we do this and then do this, versus something that looks like this, where we do this and then we do this. And so here, 0, this would be 0 order. This is the order for this. First and second. And so you pretty much can eyeball it, you know, and see, you know, about how long did it take for it to be consumed. Sometimes we don't have enough data. If we don't have enough data, let's say we just have 3 data points right at the beginning, this. And then 3 data points right at the beginning. So we aren't waiting until half of it gets consumed. And 3 data points right at the beginning. Here. Can we still figure it out? You know, we didn't collect the rest of the graph. And so everything else is missing.
We could probably still figure it out, but it would be harder.
It would be harder, for sure. Yeah, we can figure it out, but definitely it's going to be harder. And so if we don't have enough data that goes to half and 1/4 of the original concentration, then we have to use another method. So let's take a look at some other methods that are available to this. One method is called the method of initial rates. So we'll call it method 2. Method of initial rates. With the method of initial rates, we don't have to collect a whole bunch of data. We need to collect the data right at the beginning of the experiment. Here. so that we can get something called the initial rate. And the initial rate is defined as the rate at time 0. The rate at time 0 is equal to the tangent, the slope of the tangent, actually the negative slope of the tangent at t0. So to get the initial rate, what you got to do is you have to have the curve like this, and then you have to draw the tangent right at time 0. And so that would be it. But drawing the tangent is difficult, you know, because you don't have the rest of the curve there. It has to be symmetric on both sides. And so to make life a little easier, we say that the initial rate is going to be defined as that, but it's approximately equal to the average rate when less than 95% reaction has occurred. So what that means is we don't have to graph it out like this and then try to draw a tangent line at time 0 and mess with that. Because if we're looking at this, it's going to make our life a bit easier, because here we just look at the data table. And so let's look at the concentration versus time like this. Well, let's say the initial concentration was 1.00 at time 0. And then 10 seconds later or something, it goes to 0.98. 20 seconds later, it goes to 0.97, say, something like this. At 50 seconds later, let's say it's a 0.94. Just made up data. All right. How much reaction has occurred up to this point here? 2% reaction. And then from here to here, this is going to be 3% reaction. And then from here to here, it will be 6% reaction. And so the best thing is, you know, we want this average rate to be as close to the initial rate as possible. And so when we look at the first two data points here, when we look at the first two data points here, then if I take the average rate, that is the slope between the first two data points, then that's going to be the one that's closest to the initial versus the first and the third, you know. Because by the first and the third, it's slowing down quite a bit. And so in order to get the initial rate, you know, I'll just take the first two and then determine the slope of that, which would be delta A over delta T. In other words, this is just, you know, the final 0.98 minus the initial 1.00 divided by the final time minus the initial. I'm ignoring units here. I should put them in. Let's call it 10 seconds. And so the units here will be molar per second. Versus if I take the average over 20 seconds, you know, it's starting to deviate more, and the average over 50 seconds for sure would deviate quite a bit more. And so what you want to do is you want to tighten up that time interval to get it as close to the beginning as possible. So this is what we call the initial rate. And the slope of this the tangent line. You can slow the initial rate. All right, what can we do with the initial rate? What we can do with this is do a simple second experiment. And so this rate is valid for what concentration?
The concentration after 10 seconds.
Well, the initial rate is valid for the initial concentration. It's only valid for the initial concentration because once you start to consume more and more of the reactant, once you start to deviate more and more from your initial concentration, what's happening to the rate? It's changing. And so the initial rate is valid for the initial concentration, and it's the rate at that concentration. And so the experiment that we do to figure out the order is this. So we'll take the initial concentration and determine the initial rate. Which we'll call rate 1, rate initial. And then we'll double it. And so if we double the concentration here, we see what happens to the rate. The rate for 2, did the initial rate stay the same? If we double the concentration and nothing happened to the rate, we call it zero order. If we double the concentration and we get 2 times the original rate, then it's first order. If we double the concentration and we get 4 times the initial rate, then it's second order. So this is basically what's happening here. We set up an initial rates table, that is the concentration and then the rate, initial rate here. And we just do 2 experiments over here. Experiment 1 will have concentration 1 and rate 1. And then experiment 2 will have concentration 2 and rate 2. And we just compare what happens here. So we start off with concentration 1 and then double it to get concentration 2, and then look at what goes on with the rate. If we double this, did the rate stay the same? Did it double, or did it quadruple? If it stayed the same, again, it's 0. If it doubled, it's first. If it quadrupled, it's second. So that's the method of initial rates. Now, why does it have to be the initial rate? Why couldn't it be some other rate? The reason it has to be the initial rate is because only at time 0 do you have control over the concentration. Because only at the start of the reaction do you have control over concentration? In other words, initially it's easy to double. If I started off with 1 molar, I could just double it to 2 molar, right? But with time, what happens is that molarity changes, and it's going to be changing differently for the 2 experiments. So I can't do it at 10 seconds, because at 10 seconds, the concentrations might not be doubled anymore, right? Because typically what happens is this: the higher the concentration, the faster it reacts. And the lower the concentration, the slower it reacts. And so they're changing in different ways so that the concentrations aren't always double throughout the course of the experiment. Okay. And so that's the method of initial rates. Then method 3, we graph. So this is graphical analysis. With graphical analysis, you get your data table. Let's say the time versus the concentration. And so we have data here. And then what we'll do is we're going to calculate the natural log of the concentration, and then calculate 1 over the concentration, the inverse concentration. So we'll calculate those. And then we generate 3 plots, 3 graphs. The first plot is going to look like this. It's just going to be the concentration divided by over time. That's the first one. If the reaction is 0 order, if it's 0 order, then this should be linear. Then this should be linear. Because 0 order is going to have a integrated rate law that looks like this. Concentration of A at time t is equal to minus kT plus the concentration of A at time 0. In other words, y equals mx plus b, and we should get a straight line. If it turns out to be nonlinear, something like this or something like this, nonlinear, then that means it's either first or second order. But let's say we don't have enough to eyeball it, we can't really see what the half-lives are. Well, you don't have to see what the half-lives are. You could figure it out without that. The way we could figure it out without that is we make another plot. In the next plot, we take the natural log of the concentration versus T. And the reason we do that is ln of A at time t over A at time 0 is equal to minus kT. If we rearrange this equation, we'll get this equation. ln of A at time t is equal to minus kT plus ln of A at time 0, just using the properties of logs. And so we end up with y equals mx plus b. And so it turns out that plotting the natural log versus time gives us a linear plot. And so we look here. If the reaction's first order, this plot should be linear. Then this plot should be linear. And so we look, sometimes it's hard to tell. And so what we end up doing is, the best thing is to take a linear least squares fit. From the linear least squares fit, that is, we try to mathematically model the data point with this straight line equation here, we get something called the R squared value. R squared value is the statistical value that is called the correlation factor. And so an R squared value of 1 means all the data points line exactly up, line up exactly on the line. And so what we want is we want an R squared as close to 1 as possible. I want the value closest to 1 for linear fit. And so what we'll do is we'll compare these two. I mean, sometimes it's easy to see. We'll look at the R squared for this, and we'll look at the R squared for this, and then see, which one's more linear. Thinking, man, it should be obvious, but if you don't have that much data, let's say you're just right at the beginning, everything looks linear right at the beginning. It's just over a long period of time that it starts to deviate from linear. And so if I only have the data right at the beginning, let's say you're missing all this other stuff, then how can you tell which is linear and which is not? Sometimes it's difficult. And so that being the case, we usually use the R squared value to tell us, and we pick the R squared value that's closest. With the R squared value, you have to be careful because, what you're looking for is you're looking for things like 0.99, at least 2 nines. If you have, let's say, a 0.90, you're thinking, oh, that's 90%, isn't it? But a 0.90 is not good. If you have a 0.85, that's bad. 0.85 is pretty much a very poor correlation with a linear fit. That is, it doesn't look so linear, 0.85. And so we make these two plots and then see which one has an R squared that's closer to 1. And that'll tell us which of these two is better fit. But we have one more possibility. And it could be 0, it could be first, or it could be second. And so second order, if we plot this, 1 over a at time t is equal to minus, or plus kt, sorry. 1 over a times 0. This has the y equals mx plus b pattern here. And so this should be linear if it's second order. If second order, a plot of 1 over a versus time is linear. The slope is positive rather than negative here. Again, the data there could be some experimental error, meaning some data is above, some data is below, so we'll just average those by doing a linear least squares fit and taking the R squared value. Linear least squares fit. I'll just abbreviate LLSF. Excel, we call this a trend line. And a linear least squares fit in Excel is called a trend line. Good. All right, so we make 3 plots and then figure out which one of those 3 plots is most linear, and then determine the order, 0 first or second, based on the R squared value. This is how we're going to analyze our lab, tomorrow's lab. we're going to just generate plots using Excel. It's quick, not too difficult. But on the test, you aren't allowed graphing calculators, and there's no computer to make plots, and so you do hand plots. But hand plots are time-consuming, cumbersome. And so if you're given this problem on a test, how would you figure out what the order is?
It seems like this, you only differentiate between zero order or first and second order. So you can first plot the graph and then see whether it's zero order or first or second order.
Yeah.
And that is like determine which is between if it's either first or second, right?
Right.
So
But how would you do? You would plot it and then do linear least squares fit? Let me give you some sample data here. Tell me. Let's look at hydrogen peroxide. Hydrogen peroxide decomposes into water plus O2. Here. And then if we look at the hydrogen peroxide concentration versus time, let's make this a YX table. Let's say on the test you're given some data that looks like this. We start off at 2.52 molar at 0 seconds. Then 100 seconds later, we end up at 2. Actually, does somebody have their book? No? Nobody has their book? Let me grab my book. I'm going to get some real data.
I don't know. Like we got on Thursday, right? I'm Thursday. I had work on Thursday morning, and then Friday, Saturday, Sunday work, and then Thursday. So then Monday, Tuesday, Wednesday, Thursday. I'll take Monday. Oh, yeah, that's the chocolate.
All right.
Yeah.
So at 200,
Yeah.
sorry, this is 200 seconds. We have 2.01. At 400 seconds, we have 172. And so, what were the methods that we have so far? What was method 1? Eyeball. Can you eyeball this data table?
No.
Why not?
You
enough data.
Yeah, we don't have enough data because we need to cut this in half, which would be around 1 1/4, and then cut it again in half. So we need it all the way to 0.75. But we don't have enough data to eyeball it, so we can't eyeball it. Even if we were to graph it, could you eyeball it? No. Not enough data. Remember, at the beginning, everything looks somewhat linear. It looks the same. What's method number 2? Method of initial rate. So we have, we could plot this and then draw the tangent line at time 0 and then measure the slope. That would be the rate at 2.52 molar. Does that make sense? But drawing the tangent line and graphing it's a hassle, right? And so rather than doing that, what is an alternative that we could do? Alternatively, rather than figuring out the slope of the tangent, we could
Graphical analysis.
not the graphical. It still was method of initial rate. We could get the average. And so what I could do is I could just get the average rate, i.e. the slope. And so, in other words, I'll take the average slope from 0 to 200 seconds. And so that's just delta y over delta x. But the problem is this. That, you could use the average as long as it's close to the beginning. Is this average close enough to the beginning of the reaction? No. How do we figure out what is close enough to the beginning? We figure it out by seeing if there's less than
95%.
Less than 5% reaction.
Yeah, less than 5% reaction, or we have 95% remaining. Right? Did we have less than 5% reaction here? Yes? No. Actually, this is about 0.5 over 2. 0.5 over 2 is about 25%. Do you see that? And so here we have 25% reaction. It's already gone too far. Initially the slope was like this, but after 25% reaction, the slope's gone way down, and then the average of that is going to be something like this rather than something like this. Does that make sense?
See that again?
In other words, if I were to graph this, I have data that's kind of spread out like this. Okay? What I want to know is I want to know the slope right at the beginning. And so what I'm going to do is I'm just going to take the slope between these 2 points and call it close enough. Is the slope between these 2 points close enough to the slope right at the beginning? No, because too much reactions occurred. And so what I need to do is I need to make sure that less than 95% reactions occurred. The closer it is, the better. So the more reaction that occurs, things tend to slow down. And so is this experiment, can I use this experiment to determine the initial rate? No, not unless I graph it. And even if I graph it, it's going to be hard to draw that tangent line, isn't it? And so I'd have to redo the experiment, but rather than collecting the first data at 200 seconds, I probably should collect the first data maybe at 10 seconds. And go 10, 20, 30, 40, and then I get a lot more data points here, rather than this huge gap. Does that make sense for that? And so I'm not seeing what the curve is doing because I'm taking data at too wide of intervals. All right, and even if you do that, if you use the method of initial rates, you have to do one experiment. The only thing we can control is this, the initial concentration. Can we control the other concentration? No, the other concentrations are just declining with time. And they're going to decline at the rate they're going to decline at. And so we don't have control over that. And so we do this as experiment 1. Experiment 1, we go 252, right? And so we could make this work if we did this. You know, if we're going to use the method of initial rates, we need to redo this one. And so, if we do the method of initial rates, this data table is not good. How would you do it? Redo it? Well, I would redo it like this. You know, well, it's okay to start at 252 and go at 0, but you got to tighten up the interval. You know, maybe 10 seconds, 20 seconds, and so that we have very little reaction took place initially. And so we call this experiment 1, you know. And then what would we do? We do another experiment, experiment 2. What would you have to do in experiment 2? For experiment 2, I wouldn't start at 252. I'd start at maybe double it. Maybe I go to 5. What would it be? 504. Double it. Right. Double it and see what happens. And so I might have to tighten up the interval here, 5 seconds, because if I double it and the rate quadruples, then the rate's happening a lot faster, right? And so what I do is I just double it and see what happens to the initial slope and the initial slope here. Okay, so I get the initial rate from this data, I get the initial rate from this data, and then I'll plug it into a table like this. It's going to look like this. Experiment 1, experiment 2, concentration, 252, 504, and then the rate. This is not just any rate, because the rate's always changing. It's just the initial rate, the rate at this concentration. So we'll just call it rate 1 and rate 2. And so what did I do? I times this by 2. What are the 3 possible scenarios here? If I double that initial concentration and the rate stays the same, that is, concentration has no impact on the rate, then I know it's 0 order. If I double it and the rate doubles, then I know it's first. And if I double it and the rate quadruples, it's second order. And so I don't have enough data to use the method of initial rates. So I can't solve this using the method of initial rates. What's method 3? Graph. Method 3 works. How many data points do I need to define a curve? 3. To define a straight line, I only need 2. And so if you only collected 2 data points, everything's going to be straight line, so you're going to get conflict because all of them are going to be, right? And so we need 3 to define it. But there's also this issue, of this. It's like a running race. Like a running race, it's hard to see what's happening because everybody in a running race is going to be clustered. Let's say it's just the start, the first 1 second of the running race. Can you see the winner clearly of that necessarily? No, because everybody's clustered together. You have to wait until after the first hour. After the first hour, then everybody's spread out. And so we have to worry about this because even though it only takes 3 data points to define a line, we could have 3 data points clustered right at the beginning. If we have 3 data points clustered right at the beginning, then everything looks linear, doesn't it? Versus this. If I took 3 data points and the first one was here, the second one was here, so it's starting to look linear, but the third one will totally dictate it because if the third one's here, then linear. If the third one's up here, then for sure it's non-linear. And so having the 3 data points spread out helps minimize the error. Also, if you have 3 data points that are clustered right at the beginning, let's say, just a small error here means, a small error here, up or down, a small error here means it could sway between nonlinear and linear just by random error, random fluctuations. Whereas a small error here, let's say I had a small error here, a small error here is not going to impact this because this is way off from linear. Linear should be way down here. That should be linear, right? And so small error here, minimal impact. Small error here, major impact. And so we have to worry about relative error. Okay, with that in mind, then we only need 3 data points. And 3 data points clustered, more relative error. 3 data points spread apart, less relative error in analyzing data. All right, and so what we can do is, well, we aren't going to do anything. We're just going to try to graph it. We'll graph it on the computer. That's method 3. That should dictate what it is. But since we aren't going to have a computer available, what is method 4? Method 4 is, and you don't need a computer. Method 4 is this. What we're going to do is we're going to generate a table. And so here I'll put the time first, 0, etc. Actually, let's go ahead and put it in 0, 200, 400. This is time in seconds. And then concentration, molar, 252, 201, 172. I'm not going to graph this. I'm just going to look at this in terms of slope. I have 3 data points here. 1, 2, 3. And then I'm going to look at the slope segments here. That is, I'm going to call this slope A, or just A. It's between the first 2 points. And then I'll compare this to B here. If this were linear, then A and B should have the same, same slope. And so we do a slope analysis here. Segment A, I do my delta y over delta x. Here. Segment B, I'll do my delta y over delta x, and then just compare the two. And so here I get the slope A. The slope A, this is just equal to the final, 201, minus initial, 252, over the time final, 200, minus time initial, 0. This is going to be molar per second. That's the slope. Then we compare it to slope B and C. For slope B, 172 minus 201 over 400 minus 200 is molar per second. And then see how well those agree. Sometimes they're going to be off a little bit because of, random error. Random error causes the data to fluctuate. Right? And so it might be off like this, or it might be very close. And so to get a better feel for this, we're going to see how well the agreement is between the two slopes by calculating something. We calculate the percent difference between those two slopes. Percent difference is just the biggest slope minus the smallest slope divided by the smallest times 100. closer it is to 0, the better. In other words, the smaller the percent difference, the more linear it is. This is the slope analysis. Or K analysis. In other words, K is just equal to the negative of the slope. And so, Ka is just the negative of the slope A. And K for B is just the negative of the slope for B. In other words, the K should be constant if it's linear. And so this is called K analysis as well. K is just the slope, the negative of the slope. All right. The next thing we have to test is this. We're going to make a table of the natural log of A, and then do the K analysis of this too. But rather than doing the slopes, of calculating the slopes, this is 1 over the concentration of A. Instead of calculating the slopes, calculate K. And so the ln of A plot comes next, and we saw that ln of A is equal to minus kt plus ln of A times 0. But instead of doing that, we're going to calculate K for segment 1. And so this is for first order. Ka for the first segment. Ka, this is going to equal the natural log of A times t over A times 0 divided by t. We'll take the negative of that. And so for the first order of this, the first segment is going to be this. It's just going to be minus ln of 2.01 divided by 2.52 divided by the time interval, which is 200 seconds. And so it just saves a little bit of time instead of doing the slope here. We just go 2.01 divided by 2.52 equals, take the natural log of that, divided by 200. And this comes out to 0.00113. How many sig figs am I allowed? Let this carry extra. KB, this is going to equal minus ln of 172 over 201 divided by the time interval, which would be 200 seconds. So let's do that. 172 divided by 201. Natural log divided by 200. 0.00779. Assuming I didn't make any mistakes. All right, I didn't calculate the slopes, did I? For the previous. No, we'll do that. But what time do we end at?
right now.
We'll do it next time. We'll have to finish this Wednesday.